Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on September 8th, 2025, which was about 4 days ago. The standout idea is an autoregressive multi-view diffusion model that generates views sequentially from any number and ordering of posed inputs, delivering flexible, streaming-friendly novel view synthesis with strong visual quality. The paper is titled CausNVS, Autoregressive Multi-View Diffusion for Flexible 3D Novel View Synthesis. And as we will see later, the implications for interactive systems are quite significant. Beyond flexibility, the method uses causal masking, per-frame noise conditioning, and relative camera pose encoding to stabilize long rollouts while keeping inference efficient. On X, reactions highlight sequential, flexible view generation and interactive streaming, with mentions of causal masking and a spatial sliding window for stable, high-quality visuals. Engagement looks modest, around 100 likes. Alright, the previous segment highlighted why causal generation matters for streaming. Figure 1 illustrates the effect. More input views lead to smoother, more consistent rollouts, and the sequence extends well beyond the training length while preserving 3D structure. The panels progress left to right as the model autoregressively predicts new frames, which demonstrates stable geometry because each step conditions on past views. The comparison across 1, 2, 4, and 16 inputs shows visibly sharper details and fewer artifacts as context increases. So, the previous figure stressed benefits from more inputs. Figure 2 shows the pipeline that makes those gains possible, combining causal training and efficient inference. The top row depicts training with frame-wise self-attention, causal masking, and relative camera pose encoding, which means attention respects time order and uses pairwise poses for stable geometry. The bottom row illustrates inference, where frames are generated sequentially using a sliding spatial window, plus key-value caching, so context stays local and computation remains low even as sequences grow. Alright, the previous figure walked through training and inference mechanics. Figure 3 analyzes how relative camera pose encoding shapes attention responses. The left panels show that attention varies periodically with rotation and grows linearly with translation, which signals sensitivity to real three-dimensional motion. The right panels, without the pose encoding, stay flat because the attention ignores pose changes. This behavior matters for stability, since pose-aware attention helps the model reuse context correctly as viewpoints shift. So the previous figure dissected pose-aware attention. Table 2 reports N-to-M ablations on Re10K, showing PSNR and TSED as input views and total frames vary. The causal autoregressive model stays steady across f equals 2 to 64 and across n from 1 to 16, which signals stable rollouts. The non-causal variant drops when f is shorter than training and drifts under autoregressive use, so its PSNR lags despite high TSED in parallel mode. So the previous figure dissected pose-aware attention. Table 1 reports benchmark PSNR across Re10K, LLFF, and DL3DV comparing feed-forward to generative baselines. The entries show that the method matches or surpasses several generative systems, with strong scores on Re10K at n equals 2 and 4, and solid results on LLFF and DL3DV. The caption emphasizes flexibility because a single model handles different input counts and long rollouts while maintaining quality. Okay, 2 takeaways stand out. Generating views autoregressively with causal masking and per-frame noise conditioning delivers flexible end-to-end synthesis that stays stable over long rollouts, and relative camera pose encoding anchors attention to real motion, enabling efficient caching and streaming. The broader implication is interactive, pose-controlled 3D navigation. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.